welcome back again. Today is the day 3 of the program. We are starting the lecture 7 and the topic is on overview of DC-AC or AC-DC power converter topologies used in green hydrogen energy system. This will be provided by Professor Jahangir Hossain. Over to you, sir.
Thanks, Dr. Animesh, and welcome everyone. So yesterday we talked about DC to DC converter. So if you remember that DC to DC converter used in both cases, like electrolyzer as well as fuel cell, right? But DC to AC or AC to DC, not used in both cases. Unless you have got other renewable generators. Then, so for fuel cell, we produce DC output, right? Then, for utilization, if you have got AC load, then we need inverter, right? So that's DC to AC, that we call inverter, right? But for electrolyzer, what do we need? We need to supply DC voltage. So we need AC to DC converter, but we also call it rectifier. So here would be mostly a rectifier and inverter. So these are the content that I'm going to talk about. So initially I will start with why actually we need AC DC or DC AC. That's I already actually mentioned. And then when you're going to select either rectifier or inverter, what actually you expect from them to be utilized either in electrolyzer or in fuel cell, right? And then we'll talk about few topology because there are so many topology, but those are mostly already utilized. I'm going to show them, and then we'll show some comparison because you always need to know like pros and cons for every topology that's available. That will help you for your particular application, which one actually you can pick up. And then I'll also touch some converter driven stability. Although we are talking about control, so before designing control also you need to know little bit about the stability and what actually makes the system unstable. Unless you know the exact reason why your system is unstable and which making the system unstable, then you won't be able to design control that gonna help to make the system stable. So you also need to know have some knowledge about stability as well. I believe you might already have it, but we're gonna just touch it. If I find time, hopefully I'll find some time. So we talk about many times that that's converter actually plays a significant role in ensuring like efficient conversion, control, and also grid integration. And for like hydrogen, mainly for like electrolyzer, we need actually high power, high current devices. So although there are many inverter converter available, but here for our application we mostly need high power and high current. So this is also already for you already clear, and I already mentioned that from fuel cell we convert DC to AC for connecting either with the grid, and even if you want to supply load, that is AC. But if you have DC, then probably, but again even if it is DC, although we are not showing the middle stage DC to DC, but again we need probably DC to AC. So in both cases we might have here like DC to DC converter as well. And in electrolyzer, as I mentioned, like at needs DC, so you need to convert from AC to DC. So as I say, like to find out which one might be applicable for certain application, that depend on like the feature of the inverter, converter, or rectifier. So again, I think that's we already covered the function and need for rectifier. So I mean, if you supply from DC, I mean from photovoltaic system, you might not need rectifier because that's already DC, but then you already need like DC to DC converter. But if you want to, let's say, supply from wind farm or any other source which produces AC, then definitely we need rectifier. An inverter, I already mentioned that if you, I mean, from fuel cell we produce DC, so we need inverter. But also, I mean, if you have any energy storage system in the devices, also, I mean, you need inverter as well. So that's, I think we already have covered. No need to repeat. Now, what actually you are expect? I mean, if you want to, find out a rectifier like for powering electrolyzer. So as I said previously, that we need like a high power rating, because as you already know that electrolyzer could be like already like in the megawatt level, right? There are kilowatt as well, but it could be gigawatt level as well. So we need a rectifier that has got significant like power capacity. And if in most of the cases what we do, that we use like many of them in parallel to, I mean, increase their power capacity. So that probably, when you have got like megawatt level, you might use like parallel module as well. And then for electrolyzer also we need very precise DC, right? Exactly, I mean, whatever voltage I mean mentioned, you need that. So that's why we need like a controlled DC current and also controlled DC voltage for optimal operation of the electrolyzer. So that's, we have to make sure that it's not only DC, but it's like controlled DC, both voltage as well as current. Another important requirement, that it has to have like very negligible ripple. I mean, if nothing, then definitely best. But as you know that most like we use like different converter, it does produce ripple. So that's why we use like filter to remove them, but it's still sometime we have ripple. So you have to make sure that for other application might be okay. If we have slightly bit ripple, although I mean we don't want for any application, but for particularly for electrolyzer, we need to have, I mean, DC with negligible ripple. And what happens when you have very low voltage and low current, even sometime it produces more ripple. So that's also we have to make sure when we're gonna use it, either in experimental system or real cases. And also like the power factor, we have to, I mean, this is mainly for like the AC side. So power factor, I mean, we always expect close to unity, but you know that in most cases we don't have unity, but we always try more than 9495, just to minimize that it does not like draw reactive power from the system, right? So what happens, like even in your home, if it draws reactive power, that means whatever appliances we have, if we have lower power factor, what will happen, right? So at then it's gonna be having reactive power. So that means but your load, mainly, whatever output you are getting from the active power. But as you know, that due to the nature of the electrical network, although we want like active power, but always there are some reactive power in the system. But we want like as close as to unity, because then you will have very less reactive power. So that's why we also want close to unity reactive power. And then the total harmonic distortion, that's also depend on the power quality. So we want very low total harmonic distortion as well. And in most of the like standard, for example, this is IEEE, and also there are IECE standard as well. But most standard needs that your total harmonic distortion should be less than 5%, right? So any device you design or you want to commercialize sell, when they do the testing, they will make sure that it's less than 5%. If less than 5% is accepted, but even lower is always better. And then we definitely want that it will have wide input voltage and also the frequency tolerance. So in that case, when you have fluctuating power from like either renewable sources or from weak grids, still your rectifier can work. Although we mentioned that we want constant, but at the same time, if it is have that wide range, and if for some reason if exceed that certain value, still your rectifier would be able to your electrolyzer should be able to work with the input rectifier. And dynamic response, definitely we want that ability to quickly adjust the DC output based on the command from the plant, either to ramp up hydrogen production, because depending on your requirement, you can anytime ramp up hydrogen production or reduce the hydrogen production, right? So in that case, your rectifier should be able to meet that requirement. So if you give command, it will increase, or if you give command, it should be reducing, but that will be done by the controller. Okay, and yesterday you have learned many of the different controller, right? So you can apply anything based on your requirement. Like PI, normally industry widely used because it's easy to design and also implement. Although you need to change the parameters if your condition changes, but there are so many algorithms also you can utilize to find the exact parameter, and if you actually find the optimal parameter, sometimes PI works much better than those very complex linear and non-linear controller. So that's the reason. Still, that's one of the most utilized controller in the industry. But having said that, some industry they are also utilizing sometimes that advanced MPC, model predictive, and in other adaptive control as well. Same for like inverter also. It would be quite similar requirement. I already mentioned that total harmonic distortion. Here also, definitely we want less than 5, and then precise voltage frequency, that is also quite similar. But also in the AC side, you need another requirement for the synchronization. For DC, there is no problem with the synchronization because there is no frequency, right? But for AC also, you have to make sure that it has got the ability to accurately detect grid voltage, frequency, and phase angle, so that actually it can synchronize when it is connecting with the grid. So that's also another requirement. And mainly those of you like works with the microgrid, that's also like when microgrid go from like grid connected to island and vice versa, that microgrid also should be having the capability, so from islanded to grid connected, so that it can automatically synchronize with the grid as well. And I believe you know like what are the requirements for synchronization, like voltage, frequency, phase angle, everything has to be same. And also, I mean, mostly probably you know that every grid, like you know either Indian grid, Australian grid, all grid they have got some grid codes. So if you want to connect any new power plant with the grid, so here, for example, in Australia we have got Australian electricity market operator. So we have to do number of tests to show that it actually satisfies the Australian grid code requirement, and same thing would be in India as well. Like you know, if you are a private or you know you are having like your own some you know power generator or a small power system, and if you want to connect, then you have to show that it compliance grid. And compliance grid again mainly the voltages, frequency, sometime n-1, n-2 requirement. Like if any of the device get disconnected, still it should be able to meet the grid requirement in terms of voltage, frequency, power quality. Anti-islanding protection, that's also like many of the devices that have got that protection there, so that I mean it can detect the loss of the main grid and automatically disconnect it to protect like an utility worker or equipment. So for example, that you have like one electrolyzer, for example, connected with some part of the grid, and if some cases, I mean if it is disconnected from the main grid, that means it is like islanding. So that devices should have that I mean sensing that grid is disconnected, and based on that the protection system can activate, like you know either to shut down or whatever, or you know working in other mode. But it has to have that capability for islanding detection and protection. Fall right through, I already mentioned previously that it should also have the ability to stay connected and supply at least even not the rated amount of power, but at least partially when there is a disturbance in the grid. So for example, let's say you have got fuel cell, it produces you know I don't know, maybe let's say 50 watt, right, 50 kilowatt, and if there is a disturbance, then I mean still I mean it should have the capability to supply partially electrical power. So I mean still I mean we don't have that many fuel cell, but for wind turbine and even many of this photovoltaic system inverter, they also have that requirement that you cannot just completely disconnect it when there is a disturbance. So you should have that fall right through capability, and grid support function for inverter, that active reactive power control, sometime voltage, frequency as well, and also with this grid forming inverter that also provide synthetic inertia to the system as well. And that's one of the topic, grid forming we're gonna talk about to the next session. Same like the other one also, I mean it should be accommodating like a range of the DC voltage that might be coming from PV or you know from fuel cell. And then if you have like you know PV, the MPPT also I mean should be connected with the PV to provide like maximum power output from the PV under any operating condition. Now so far, like for electrolyzer to convert from DC to AC, in the most of the existing like electrolyzer, it used like 12 pulse or 24 pulse rectifier. Now in China, I'll show you the next example. They already have a big electrolyzer, and they are actually using those like 24 pulse, not 12 pulse, but the 24 pulse. But mostly like you know 12 or 24 pulse rectifier actually used for electrolyzer application. Any of the rectifier could be Thyristor, IGBT, and also sometimes diode as well, right? and you know, like the difference between diode and diode is definitely uncontrolled, but if you have thyristor, it would be like a controlled rectifier, right? So we are not going for that basic principle of rectifier, because you already know from, converting from AC to DC. But what we have it here, you can see that here we have initially in the grid side a filter, then we have got like 12 pulse transformer, but if you have got 24, then also you need like 24 pulse transformer, and depending on the how many pulse, you will have the phase angle. Now here you have got two 6 pulse thyristor, which are connected in the two secondary side of this low frequency transformer. But again it's not that always you have to use low frequency transformer. So the existing one has got low frequency transformer, but as you know that people also working for other transformer, and Dr. Animesh yesterday mentioned that SST, that's like a transformer with power electronics that even has got better, not only stepping up or stepping down, but also it has different control capability as well. Now here you see that that silicon control rectifier, you have got this firing angle alpha. So by adjusting the firing angle, you can actually control the current, and depending on that, also what angle you are operating, depending on that you're gonna get like in the output voltage and current. But when you have got very low amount of current, actually it produces more harmonics. So that's at the low power operating condition, actually it produces more harmonic, because that time also have got reactive component as well. And as you know, harmonic, as you know that we have got like third harmonic, fifth, like and so on. So by using this Y delta configuration here, that actually when you have got that configuration, although you are not going in the transformer connection, but with that connection actually it can actually cancel or eliminate fifth and seventh order harmonics from the current. And then by using that transformer trap filter, it also actually eliminate 11th and 13th of the order of the line frequency that are commonly used for power to hydrogen converter based on this 12 pulse thyristor rectifier. So from here, this pulse coming here, and from thyristor, then you are getting the DC, and then again this this capacitor again used to eliminate the ripple from the output voltage. And then again we are not showing DC to DC converter, but you might have DC to DC converter as well, and then we can supply to the electrolyzer to produce hydrogen. So we already talked about that it can suppress these harmonics, that improves overall power quality and reduces filter requirement, and this is well suited for large electrolyzer. Output voltage can be regulated by using the firing angle, because when you we are not developing the equation, but when you have that equation, you will see that in the output there is a relation with the alpha. So by changing that alpha, you can easily control that output voltage, and it's already like proven technology in the industrial environment. But here definitely one of the limitation is that this transformer actually very bulky. That if you have like megawatt level transformer, the conventional transformer, it's actually bulky and you might need big vehicle. I mean, even if you want to take it from somewhere, and this is not even cannot provide bidirectional. It has got slower response compared to active front end converter. That's probably going to talk about later. And power factor also goes lows when you have got lower output voltage and larger firing angle. So definitely, I mean, if you remember the sine wave, so when you have got like lower firing angle, so that means you get higher voltage, but higher firing angle you get lower voltages, because the relation like cosine of alpha. So that's like the first configuration. Now the next one, so here also I mean we have like 12 pulse transformer, but the difference here you can see here that here we have got like this DC to DC converter that we already talked like previously, and that interleaved buck is interleaved DC to DC converter. Now when this like when you have this like DC to DC converter, the main advantage is that you can have like high quality power output compared to the previous one, because it has got very good control capability that we already mentioned previously. So definitely the biggest advantage, the improved power quality, like in terms of lower distortion and also better power factor over the wider range of the power to gas converter. And it definitely, as you have got those filter and other things, so it can also eliminate those harmonics as well. So here, although it's going to be a little bit more expensive, but this one can provide better power quality. So definitely, I mean, low total harmonic distortion, no extra power switches in rectifier, voltage current regulation, improved power quality, and also it's scalable and modularity as well. So you can add more capacity, I mean, if you need in any point of the time. And when you have this, definitely it has got benefit for the electrolyzer operation in terms of lower stress, heating, increased reliability, reduced switching losses, and also it allows precise control, less filtering required, and better compliance with the grid code. And the last one here is again we have got additional device. I mean, if you compare with the previous, I mean the first one, that we are adding additional active shunt filter, because as we mentioned that at the low current we have got like higher harmonics as well as a total harmonic power quality issue. So here we can even reduce that by utilizing another shunt active power filter as well. So that's the difference, I mean, if you compare with the previous cases. So again, that's low total harmonic distortion with that shunt filter, and once we have got low harmonic distortion, that it's going to also reduce the reactive power losses, and definitely that's going to be grid friendly, and it will improve power factor. Definitely it will comply with the standard and grid codes. Now if you compare, there's like three different topology that we talked about. So here this one actually comparing the power factor for the electrolyzer. So initially this is like at the beginning of the lifetime, and this one like more on the end of the electrolyzer lifetime. Now which one we showing the best performance? That configuration that we mention here, that one of them has got shunt filter, other one we have got this multi-phase chopper with the diode rectifier. So here if you see the dotted one, that is showing the best performance. So the power factor is not unity, but it could be like 0.99, right? So the second one, which has got that DC to DC converter, that is also, I mean, quite good. Although at the low current, it has got slightly bit lower power factor, but then I mean, it's quite good. But if you see here, the initial one, only Thyristor rectifier, it has got very low power factor, mainly when you have got the low current, right? But you might ask, like, why it's showing better performance here, right? So whatever power factor you can see here at the end, I mean at the beginning of the electrolyzer installation, but we are getting higher when it is like more at the end of the electrolyzer lifetime. But it should be other way, right? Normally we get better performance in the beginning, right? But the reason actually here, because what happened, like that's the, I mean, if like when they actually goes at the end of the aging process, the increase in the electrolyzer resistance. So when we use for a longer period of time, it actually increases the resistive value, right? So when we have got higher resistance, what will happen? Power factor will be increased, right? So that's the reason, I mean, here, although I mean other you know I mean performance parameter might degrade, but the power factor actually get better due to increasing the resistance. So that's the reason. So here, I mean, again I have given all the explanation that, I mean, if you consider the power factor, which one is like best, which one is the middle, which one is giving poor performance, mainly when you have got the lower current, but definitely there is a difference in the price. So depending on your requirement, I mean, you can pick up, like, you know, which you're gonna you know utilize, and even if it's not that, I mean, you cannot use like, you know, 12 pulse Thyristor rectifier. So when you have got like, you know, lower power factor, there are other option as well. You can still improve power factor, right? Using, but the requirement is that you have to use additional device, right? And there are many like device available in the market to improve power factor, right? For example, like people use shunt capacitor. People can also use flex devices like, you know, static var compensator, which is called SVC, and also like other components called static synchronous compensator, which is called StatCom. But again, I mean, you have to invest, like, you know, to buy those devices. But the solution is available in the market, even if you use the Thyristor, you know, rectifier. So, but at the end, that's gonna also increase the overall cost. So you have to find out that if I use 12 pulse Thyristor rectifier plus SVC, what would be the cost compared with only I'm just using the third one for rectifier. What about the total harmonic distortion? So again, if you see that the one with the shunt power filter, that's giving the lower total harmonic distortion, in both cases, either in the beginning or end of the electrolyzer lifetime, compared to in both cases. So none of them within the 5%. So definitely you need, probably if you use this, you need additional filter to bring them back below 5%. But this one is already below 5% for total harmonic distortion. Yeah, so that's, we already talked about that comparison. So again, this one even giving like a better picture. So not only a power quality, but also efficiency, control, reliability, cost. So again, this would be slightly bit than higher cost than that. But some of them have, because this is more like established technology, so it might have very good reliability and also good efficiency as well. But in terms of power quality, this is poor. So again, as I say, like which parameter is more important for you, based on that, you're gonna pick up which one is the best solution for a particular project. Now the next one is quite similar, but here it has got like 24 pulse, and instead of using the normal low pass frequency, here they are using load tap changing transformer. So have you heard about this one? Probably you know about that, right? And why we use like load tap changing transformer? To control voltage, right? So when voltage goes beyond the required boundary, the tap automatically changes either to increase or decrease the voltage. So here also, if you use this one, it does have this additional function, and also like using this one and then Thyristor angle, you can also try to maintain the requirement for the power quality and power factor. So this one actually serve both purpose, not only like the producing the phase shift, but also it has got on-load tap changing option as well. Because sometime only a single device cannot meet the requirement, so multiple Thyristor again might be connected in parallel. Now if you compare like the overall efficiency, so only the Thyristor rectifier, they are having efficiency almost like in the more than 99%. But if you consider the losses in the transformer is also highly efficient, but then overall efficiency would be here around 97%. But as you know that for converter, inverter, now there are so many in the market which has got very, very high efficiency. So the overall efficiency is still here more than 97%. What else? This one also have good control over the electrolyzer current and power, so that can meet the requirement for the electrolyzer. And this sorry, the next one is not the Thyristor, this one actually IGBT. So this is like the IGBT rectifier, and then you have got IGBT converter as well. So using this one, again, I mean, this one has got the better control capability compared to the previous one, as we discussed in the 12 pass cases as well. So this one efficiency, I mean, compared to that one, slightly less, because you have got again DC to DC converter. So with that, again, efficiency is more than like 98%. But when you do the combined efficiency, it would be around 96, 97%. This is the last one. Here we have got diode, like as we mentioned in previous cases, but here we are not having any like active power filter. But other than that, I mean, we do have transformer and then rectifier and then converter, and then we are applying power to the devices. So this one also have optimizers like the power quality, mainly providing high power, high current applications, because as we talk many times, this has got very precise control over voltage and power, this converter. So that's why it gonna produce good control input voltage to the electrolyzer. Now this one actually, I mean, as I say, in China they have already installed, and they have experimental result as well. They published, and they provided some cost comparison in their own currency. So you can see that definitely IGBT is would be slightly more than the Thyristor, but all the comparison between these two rectifier is provided in terms of DC output power, rectification efficiency, AC output power, but both of them 5 kilowatt. So it's same capacity, so that give you like a good comparison. So that's all about a rectifier. Now we're gonna go for inverter. Now again, also, I mean, there are so many inverter technology you will find in the market, and inverter used not only for fuel cell, but other grid tied generator, battery energy storage system. But again, the function is always converting from DC to AC. So it could be the DC from either fuel cell, DC from PV, or even DC from the battery. Some of them single stage, some of them multi-stage, some of them unidirectional, some of them multi-directional, even some of them have multi-level. We have also either current source or voltage source, which is more grid following and grid forming. So there are so many technology available, and this is also, I mean, there are established topology also used for the inverter as well. But here for the fuel cell application, definitely the requirement would be that first we're gonna be boosting, and then we're gonna maybe converting from AC to DC, because fuel cell output voltage might not be that high, right? So before applying to the inverter, we might boost the voltage first, and then we convert from DC to AC. So in most of the cases, we'll have a single device, which is the combination of a boost converter plus inverter. And there are already available in the market that the single device using one shared leg, it can does both like boosting, and then it can invert from DC to AC. Now again, I mean also like whatever converter use, we expect some features from them as well. So mainly, I mean, if you thinking about going for islanded application, we'll think that it have like grid firming capability, but if it is connected with the grid, I mean, we might not be needing that feature from the inverter. We also expect like the fast dynamic response if we want to provide ancillary service to the grid, providing voltage and frequency support. Definitely, like all other devices, it should satisfy the standard in terms of the power quality, as I mentioned, less than 5%, and also it should provide voltage regulation at the point of common coupling. And when we are using the solar, I mean also it should be doing like the MPPT as well with the DC. Now here you can see one of the solution, I mean, for using in the fuel cell. So if you see here, like this is like that inverter, right? So just probably better would be, I mean, instead of discussing this one, we'll discuss using this one. So here, I mean, if we not, because that one already combined, if we not combine, what will happen? I mean, you see here, up to this portion, like this leg, this is like DC to DC converter, right? So this diode D1, MOSFET S5, and then this inductor LB, and this input and output capacitor. So this portion is nothing but like a boost DC to DC converter, and then the remaining portion, that is like a with the filter. This is like the inverter, right? So why we need that for fuel cell application? Because as I mentioned that fuel cell output might not be enough, just after inverter to match like whatever the requirement voltage in the AC side. So that's why always we use a boost with the inverter. Now here, I mean, if you see like this branch, actually what will happen, I mean, instead of using this one, so like this D1 and S5 actually can be actually substituted by just like by using like a another just like another MOSFET. So that's why like in this, like one of them could be common for inverter as well as converter as well, and that's why like for particularly for hydrogen application, I mean this type of, I mean if it is single stage, this type of topology used for both boosting as well as, here you can see that we replace the previous one, only using this common leg for like both converter as well as inverter. And definitely if we have that, that's common in terms of like providing control. We don't need like separate control for, I mean, DC to DC and then inverter. So in terms of control, in terms of efficiency, and it's like one integrated power stage. So this gonna be like better solution if you, I mean, use that inverter topology mainly for electrolyzer applications. And again, I mean, it's gonna be taking quite a long time, and if you want to see like all the voltage current waveform, but as you know that for all those like switches we have. To operate that, we need the pulse we can apply, but I mean nowadays, I mean it's not that difficult, I mean to get those pulses. But here the good thing is that still you can see the inductor waveform, which does not have, I mean, current, I mean low frequency current ripple. So that's in that sense actually provide, I mean, good output. But again, I mean, what will get output is not exactly sine wave, as you say, like you get like a square wave, but you know that when you use like 3-phase multi-stage, I mean probably you can still you will have some like harmonics, but you can get more close to the sine wave. So again in the market, I mean people, as I say, like they are working multi-level inverter. We have also 3-phase. We have like an impedance source 3-phase. It's not like that. There's so many topology available in the market. But as I said, that only requirement in this case that we whatever topology you're going to use it, it should be like a DC-DC, and then it produces pure sine wave. That would be the like the best solution. So and if you use that H bridge, then number of depending on the number of bridges, you're gonna have like harmonic distortion. More is always better because it would be more like close to sine wave, as I mentioned. And for utility scale application, definitely we'll be preferring like multi-phase H bridge that gonna give like better application for grid application. But if you have got like a small size, you don't care, then probably you can go for lower bridge that gonna reduce the price, but you have to compromise with the power quality. So I'm not showing like all the inverter because as I said, this is quite established, and I mean you already understand the requirement. So I'm just take like few minutes, then I'm gonna finish and we will go for question answer. So again, probably like before going like the converter stability, just like what are the different stability problem you might have when like all those DC, AC, DC, DC and different converters that we mentioned that's connected with the power grid. Because like in recent year, that all the generator, all the storage, even like the different loads, all are connected like with inverter converter. So that's why if you go like 5 years back, we have only this. At the beginning, if you think about 10-20 years back, we have only problem like rotor angle stability, and rotor angle stability only involves the stability problem with the synchronous generator, right? And then because what happened like previously, most power grid they operated very conservatively. Conservatively means that if like let's say one transmission line having capability to transfer let's say 20 megawatt, then probably they were transmitting only 5 megawatt or 10 megawatt. So they are always operating like 50% of their maximum capability, because the reason that power company they don't want to take any blame, that if something happen, at the end the system gonna be blackout, and there will be so many issues, not only from the people but from the government and so on. So that's why they are very conservative. But what happened, when we only utilizing 50% capacity, what problem we'll have? It gonna increase the power cost, right? Because as a consumer, whatever price we are paying the price not only for energy utilization, right? We are paying price for energy generation, like high voltage transmission, and then distribution, all the costs add up when you are paying the electricity bill, right? So when the utility use like 50% capacity of any devices, so we are not, utilizing, maximizing the whatever, capacity available. So at the end, it contribute to give like higher prices, right? So that's why what happened in recent year, as the electrical demand have gone up significantly in all countries like India, Australia, everywhere, because it's not only residential demand but also demand from like different industry, and all the other sector they are also like electrified, like agriculture, health, education, and so on. So that actually increases the demand, and to meet the demand, it's not only enough that we have got building like new power plant. So the most challenging part to building the new transmission line, because it takes time, right? And also it's quite expensive. So nowadays what happened, they are trying to utilize whatever maximum capability they have, and that actually increases the possibility of not only the angle stability but also the voltage stability, frequency stability. And not only that, when you have got different power electronics component, they actually introduce two different new type of instability. One is called resonance stability and another is converter driven stability. Now people who are working now mostly in the power electronics area, they look for always this either resonance stability and converter stability. But also the voltage and frequency stability, that's also getting common, because as I said that there are so many induction motor in the system, and also like variable generation and the load demand have gone up significantly. Most of the equipment they are operating close to their limit. So that contributed like now thinking like to develop robust control and other even like advanced level non-linear control, even just to make sure that we can ensure stability. And not only that, we also having like different monitoring, online monitoring, that also help us to see like how the system is operating. Now also when you're gonna go for stability and control, also you need to know like the devices that you are using, what like the time frame actually they are working. So as Dr. Animesh yesterday mentioned that when we design control, we have to think like the bandwidth we need, right? So the bandwidth at the time and frequency, that the relation is just like the inverse, right? So here, so if you are more interested like inverter driven stability, and then you are dealing with millisecond. But if you just go for like the synchronous, like starter, that would be even like tens of millisecond. But if you go for the rotor angle dynamics, which is we called electromechanical, even that like in the like tens of like a second. But even if you go for like other thermodynamics, it's like a longer time frame. So what I'm trying to say that depending on your requirement, also when you're dealing with the model, when you're dealing with the simulation, you have to use different types of model, different types of simulation. For example, if you are more interested to see power electronics dynamics, then you have to model in this time frame, right? And also you need to do simulation that's electromagnetic. So you have to do the simulation that is electromagnetic, not electromechanical. So the electromechanical only for rotor angle dynamics. That will, if you do like RMS simulation, that will never capture your power electronics dynamics in your simulation. Okay. So What I'm saying that, I mean, depending on your requirement, the control dynamics, you have to pick up the right model and you have to pick up the right software. If you, I mean, do your own coding, that's always fine, that you just write the mathematical model and then you do coding. But if you use the existing software, I mean, MATLAB, I mean, they can do both RMS and, you know, electromechanical. But if you use PSSC, that cannot do electromagnetic. PSCAT, it can do like, you know, electromagnetic. So be careful that, for example, if you're trying to show like, you know, inverter dynamics and you're doing some simulation which actually does not capture the dynamics of the system that you are using. Probably you already know, like, you know, what is voltage stability. I mean, it's just to maintain the required voltage. But sometimes if it goes like, you know, that is continuously increasing or continuously decreasing, that actually shows instability. But also when you work with the system, from your experience, you might know that this system has, I mean, problem, I mean, voltage stability. If something changes, it can have voltage stability problem. I mean, from your experience, you will be able to find out just showing like low voltage profile, heavy reactive power flow if you do the, you know, load flow, or inadequate reactive power support, or if the system is heavily loaded. I mean, if the system goes unstable, that might be a voltage stability. Rotor angle, you know, that just maintain the synchronous operation. There is a, like, again, I mean, you can ask, like, for example, let's say if the system like here goes unstable. So at the end, whether it's voltage, whether it's frequency, its system is unstable, right? So in fact, actually, I mean, when the instability, I mean, there is no actually classification. Instability, unstable means unstable. But the reason we classify, because we need to find out what actually causes the system unstable. Is it voltage which initially introduced the instability problem in the system, or it is angle, or it is frequency? So once you know, then you will be able to develop the solution. But at the end, if frequency become unstable, voltage will also become unstable, and vice versa. If voltage become unstable, then frequency will also become unstable. But the important thing that which one, I mean, initiating the process first. So that's the reason, I mean, we classify, we do so many different type of, you know, analysis just to understand what the, like, you know, basic stability problem. So that's why we do all those classify that I have shown previously, just to our own understanding and develop the solution. But again, I mean, as I said, like, from once you work in the power industry and also do research, I mean, from your experience, you might tell that probably, you know, that actually causes the system unstable. Even from power system like configuration, sometime you'll be able to say. So if your system having like that generator which is connected with infinite bus or in a big power system, here your system will never have voltage stability problem, because, you know, so the generator has got capability to control voltage. Here also you have got number of, you know, generator. But if the configuration is like that, that you have generator and then you're supplying power which is quite far using a long transmission line, and if this sort of system have problem, you will see that this might be a voltage problem, because here there are no, you know, support for voltage. And then the finally the, like, the frequency, as I said, like, you know, in recent year, due to having like low inertia, as all the devices acting very fast, we are also having, you know, imbalance between generation and demand. So once generation and demand varies, you know, you will have, you know, either frequency up or frequency down. That means frequency issues. So I need to stop. So again, I mean, I do have few slides, but I mean, you know, you can read about that resonance instability, that's mainly happen due to that, subsynchronous, resonance, like, the resonance, right? XL equal to XC, right? So that resonance could be between like His compensation or electrical behavior of the generator, and sometimes we have like, the mechanical resonance as well between the mechanical torsional frequency and also the, turbine generator shaft as well. So mainly here, when you have got offshore wind farm connected to the transmission grid, you might have that problem. And then for the converter again, so the way that we design the control, considering that bandwidth, but sometime if your converter, like, as you see that we shown previously that the frequency range and so on. So sometime your converter and, and other devices have quite similar range, and then they interact each other. Then sometimes they also introduce, like, that converter driven instability. Normally converter do helps to improve stability, but sometimes due to that control negative interaction between each other, it might also introduce instability in the system. Anyway, thanks for your attention. I'll stop here. Thank you.
Thank you, Professor. So we'll take quick 5 minutes question, then we'll start the next lecture. Any questions from the audience?
Hello, sir.
Yes.
Sir, for the rotor angle stability, actually, the fast transients have to be neglected when we design a converter.
The converter.
It doesn't accept only, it doesn't trace out only.
The converter driven instability, you need to consider that converter dynamics when you are modeling. Otherwise, you will not see like the that problem.
Yes, sir.
In
so
the
can you suggest any reference wherein the design of that converter, how do we model it for such study?
Well, there are actually a number of reference available. I'll definitely, email some paper to Dr. Animesh and he can share. And actually, I'm giving all the slide
Yes, sir.
to him as well. But definitely, I will include
So
some
that
paper.
one paper what you shared, 2005 one paper.
Yeah, I'll share some other good paper as
Yes,
well.
sir. Yes, sir.
Yeah.
Thank you.
Thank you.
So one more question. What is the voltage instability difference between the entire grid and the microgrid? How does it differs from microgrid to the main
Can you
grid?
please repeat it?
Voltage instability difference.
Voltage.
Voltage instability at
Yeah.
microgrid and the main grid.
Yeah, as I said, like voltage instability, microgrid might have, but the microgrid, more challenge in the, frequency than voltage, but it could have like, voltage problem as well. But again, the voltage problem mainly happens when in the system you have got many inductive load in the system, because you know that what happened, like when you have got inductive load, even like in your home, sometimes you see that you turn on the switch and suddenly your power disconnected, right?
Where it is more severe, sir, whether in microgrid or in the main grid?
What is the microgrid? Definitely in the microgrid, because when you have got
Voltage
main grid,
instability is severe at the microgrid.
yes, in the main grid, there are so many, big generator and many voltage control devices as well. So definitely, in most of the cases, it will be controlled by the, big system. But when you have got the small system, definitely, the microgrid will have more problem than the, the main grid. But the thing that I was explaining, that when you have got more, inductive load, induction machine load in the system, that might causes the instability problem. Because what happens, like when motor starts, it, to energize the magnetic field, it takes more reactive current from the system, right? And when take more reactive current, that actually causes voltage in the system, and that introduce voltage. And again also, those of who are doing the voltage stability also depends, like whether it is short term or long term. Short term, the phenomena that I was explaining, that's short term, but sometimes voltage instability can also happen long term voltage instability due to that OLTC and over excitation over excitation in the generator as well, exciter.
Okay, thank you, Professor. So we'll start the next lecture in 5 minutes.
Yeah.
Yeah.
Start shortly, so be back quick.
And back in 5 minutes within. Okay. Yeah, in maybe 5 minutes within. Okay.
Maybe 2 minutes back. close. Okay.
So welcome back. We'll start our next lecture, which is basically about the controller for the inverters that can be used, inverters or rectifier sequences that can be used for either fuel cell or electrolyzer. So mostly we'll discuss in common how to control those inverter rectifier as in the grid following mode. Okay, over to Professor.
Thank you again. So again, I mean, if you remember what we discussed before, that inverter needs for electrolyzer or fuel cell? For fuel cell, right? Because fuel cell produce DC power and then we convert it from DC to AC. But again, I mean, for electrolyzer we need DC input, right? So itself for electrolyzer we don't need inverter directly, but if we have other devices in the system, then we might have inverter in the system. But when here we are talking about grid following or grid forming, we mainly think about only if that hydrogen, then it's a electrolyzer. But when you have got other system, then the electrolyzer would come into the picture. Okay, but here even if you see that simple diagram, we will understand what's the difference between grid following and grid forming, right? So when we have got a big a grid, and if your grid is strong, then normally the grid following inverter is more than enough, whatever device you're going to connect with the grid will not have any problem. But when you go for the microgrid, mainly off grid mode, or you have the main grid but the grid is relatively weak grid, then we need actually grid forming inverter. Because you see in the grid following inverter, it just follow reference power whatever you are giving. So always our intention to inject either only real power, or it could be, if you want to control it, it would be both active and reactive power. You don't care about voltage, frequency, when it is connected. But here, and definitely that's operate in the current source mode. It's a current. If you remember that we talk about a voltage source inverter and current source inverter, so that's a operate a current source inverter. And when you current source, definitely you know that there is a in parallel impedance. So that's how we electrically represent the grid following inverter. Grid forming inverter is a voltage source inverter, and here you see that we have got input not only power but also the voltage and omega, which is frequency, right? Because omega that twice pi f, so so it does have the capability to control voltage frequency, and later we'll see that it does not need any PLL because it actually form the grid, so it produce that one, but for GFL we normally use PLL. I mean, from by measuring the voltage current from the frequency, and then we use that one. I mean, for the control purpose. So these are like the few things that we're gonna talk about. Mainly the role and application of grid tied. Sometimes I mean normally called inverter, but sometimes we call converter as well. What is GFL? What I mean, we already talked about types, some application like architecture, advantages, limitations. I mean some scenarios, some real project that is actually happening with I mean grid following and I mean grid following. I mean we don't need any special project because that's already quite established, but also some project happening with the grid forming, and then finally we'll conclude it. So we already talked about rectifier inverter. I mean we don't need to repeat it. We already talked about AC DC, DC AC and their applications. But here I mean although we have like different types of converter, but like core component in the grid, now in the they are the like the core component in the modern grid, because as I said there are so many power electronics devices using. So at some stage probably still I mean it's not that power electronics actually dominating the grid dynamics, but when you have got 70-80%, they actually dominate the dynamics. At that time definitely we need to do the electromechanical, I mean electromagnetic simulation, not electromechanical. So the inverter I mean is operate either in a grid following or grid forming mode. That's also probably we already covered most of them, like yeah, I mean step up, down, that's also we already talked about. For renewables also I mean we need to convert in different phases, that's also we have talked about. And if you have got in the system like the DC fast charging, that also I mean use the rectifier, and if you have high voltage DC, that also need the conversion as well. And then it also use like when UPS, microgrid, or vehicle to grid technology. So in all of the cases I mean we have the applications of that inverter converter for grid connection. So as I already mentioned that GFL control makes the inverter to follow the grid voltage and frequency just like a listener. So it's just like a follower or listener. Whatever the grid does, it will just follow the grid voltage and frequency. It will not providing any commands to the grid to follow the inverter itself. So that's why it's just like a I mean grid are the like a leader, and GFL you can think of that's like a follower. And so here you can see that I mean if you have the grid and if you have the inverter, I mean magnitude could be different, but exactly it gonna follow. So that's like a grid following inverter. And then as I talked that we need PLL to synchronize with the grid voltage. So it tracks like voltage and frequency, and use that for that purpose use that PLL like I mean whatever the reference you are getting from that, it gonna produce that reference, and then from that whatever the current controller we use, from that I mean using that theta it gonna produce the control signal for the inverter. But as I mentioned previously, it just sends like active and reactive power to the grid based on the grid condition. So if you give like unity power factor, then definitely it's gonna give only active power, But if you have non like unity power factor, then we will give both active and reactive. Although I mean, as a honor, your preference would be unity power factor, because then you're gonna get maximum benefit. Because still, I mean, what happened, like if you have a rooftop PV in your home, only you will be paying for your active power that you're gonna sell to the grid. But if you give reactive power, still, I mean, there is no reactive power market, right? So you're not gonna get any payment. But sometime for the grid condition to stabilize the voltages, you are actually forced to give some reactive power. But when you give reactive power, what happens? You are compromising with your active power, right? So let's say if your capacity is 10 kVA, if it is unity power factor, you can get 10 kilowatt. But if it is 0.9, you will not get 10 kilowatt, because active plus reactive, that's actually get the whatever rated capacity. So you're going to be compromising. So that's why we normally prefer to give only active power, but as I say, sometime you control for both active and reactive as well. So again, I mean, yesterday when you saw that all the control, most of the control we design, is it in ABC frame or in DQ frame? In DQ frame, right? Because DQ is mostly, although I mean our voltage current is sinusoidal, but when you convert it into DQ, it operates like a DC, right? And it's easy to design the control. And again, I mean, I'm not going to talk about now, but you already know that we need to convert from ABC to DQ and then vice versa. So that, and for the conversion also we need that angle theta. So using that one, I mean, we do that conversion, and then whatever control, sometime we have got, as yesterday mentioned, that in many cases you have got outer and inner control loop. Sometime you also have only one loop, but based on that, I mean, then we design control. But here what it says, that when you have got this grid following inverter, the PLL dynamics, that actually plays significant role in your transient and also in your system stability. So you need to consider PLL when you're gonna be dealing with grid following inverter. And the voltage that here you are measuring, if it is get distorted, actually it significantly affect the PLL operation, and that sometimes also affect the system stability as well. So again, I mean, there are many PLL also available in the literature, but just the very simple one, it does have problem when you have got distorted voltage. But if you have got pure sine wave, no problem. But if you have got distorted, there are many different types of PLL, but still the PLL has got problem when you have got like distorted voltage. In that case, I mean, it might affect the, as I said, like transient and voltage, I mean, system stability. So here, like the in grid following inverter, so the current control mode actually regulate the inverter output by tracking that reference current, and this reference current again, I mean, come from the reference active and reactive power. So one of them is related to active, another one is related to the reactive. So D axis, which is mostly like active power, and this one is like the reactive power. And then from there, whatever output we are getting, we then convert from DQ to ABC, and then we apply it, I mean, to produce the control output from that pulse width modulation, right? So it actually control the duty cycle and also some angle, sometime angle as well. And by controlling that, I mean, you can control the, you know, active and reactive power. So this, I mean, mostly if you classify all the grid following control, then as I said, this is definitely current source control, but you could have either grid feeding or grid supporting, right? So if it is grid feeding, that I already mentioned, like PQ control, it's just feeding the power to the grid. But if you want to support grid, then sometimes people use like the droop control or, you know, voltage VSC, I mean, it's like virtual synchronous machine type control as well. So again, I mean, if you grid supporting, then I mean, grid is by dynamically responding to the grid. Droop control, that actually probably that is one of the very, I mean, established control technique that's available for like an inverter. So mainly used to share load using either power frequency or in some cases both power frequency and voltage reactive power droop as well. But again, I mean, there are so many droop also available in the literature, and this is current controlled. That's try to emulate like a synchronous generator inertia and damping for frequency support. So PQ control, I mean, this is mostly the simple PI control. That's Dr. Animesh talked yesterday, that proportional and integral, and both proportional and integral has got their own function or own control purpose. So one of them will try to reduce the steady state error, right? Another one will try to be messing that, you know, overshoot and settling time. So again, I mean, how to determine this KPKI, there are so many technique available in the literature, and also it's not that always you have to do it manually. Also auto-tuned PI control is also available in the market as well, I mean in the literature as well. So depending on the system condition change, it's automatically update I mean this KPI and KI based on the system operating condition. But I mean, once you have that, you know, the model, state space model with 4 matrices, you can easily do the transfer function, and then by using, I mean, root locus, and there are so many other way, I mean, Ziegler-Nichols, and there are many actually techniques that's available to determine this constant. People also sometimes try to do trial and error, I mean, to find out what the base parameter, and then nowadays even like, you know, AI and other things also can be utilized to tune the control as well. But this is one of the control that used for like, you know, PQ control for the inverter. And if you have a like a droop control, so you know, like frequency and power, I mean, the relation is given by a droop. So by changing that, I mean, droop coefficient, this is for like frequency and this is more like a voltage. Then again, I mean, you have that reference, you have measure from that, you will find whatever like, you know, change in that signal that's coming again with the measured power, and that's how you produce the reference frequency for your inner the current control. Again, here we are using the same PI that I have shown in the previously. So the only difference here that you are using to droop, I mean for that power sharing purpose. So when you have got multiple device, I mean how they're gonna share power, and when they have got like changes in the load or changes in the even like generation, this gonna be automatically changing the droop to change is like output power depending on the voltage, depending on the frequency, and that's how try to improve the dynamic performance as well as system stability. And then this like emulating the synchronous generator like characteristics. So probably all of you know like that well established synchronous generator model. Sometimes they just capture that electromechanical dampings, electromechanical dynamics, but sometimes they also try to include like voltage as well. But here I think this is only that inertia damping, that using that well established swing equation, where you have got like the damping, frequency and real power. So by using that equation, you're gonna include that one in your control in such a way that by using damping, inertia, everything, it gonna be producing that like input signal at the end to your controller. So as it does include those parameters, it try to actually mimic the behavior of the like synchronous generator. Now in terms of like so those some of the control technique that use, but as I say, like there are so many other also available in the market, in the literature, because market, I'm wrong, market mainly actually PI control, but like the literature you will find so many different techniques people have already applied in their designing, but in terms of like commercially available, mostly you will find PI. So it does like widely utilized in different like renewables. Now mostly now even in the like the power grid, if you see like mostly all the photovoltaic system and then your wind farm, they actually have this grid following inverters. But some of the battery, they have grid forming. I know in Australia, none of the photovoltaic system or wind farm, they have got grid forming. Only some of the battery, they have got grid forming. So far, the commercially one available only for the battery. But I'm not saying that it cannot be done for other devices. It can be done, but so far, that's the scenario. So even like as I said, not all the base has got grid forming. So if you have grid following, it just manages the charging and discharging while it maintaining the synchronization with the grid. And their main purpose is not like participate in the ancillary market, but mostly like support like the peak shaving. If you have got energy either deficiency or like surplus energy, then charging and discharging. So that's how they support the grid. So if you use like the battery, this is one of the way you can use that GFL with your inverter. So here you're measuring voltage and frequency from your PLL, then you are using your droop, but this one definitely you're going to provide the some control function, otherwise you don't need the droop. You can directly go for your normal control that I mentioned. But if you want to provide control function to the grid, then you can have this, and then at the end, I mean, you can have your like in the sometime double, sometime could be like only single, that inner control loop, which is mainly actually control through your pulse width modulation, and then provide whatever service you need for the grid. So here that base definitely provide active reactive power, support to voltage and frequency under grid following control, not like grid forming. Yeah, sometimes also can contribute like frequency fluctuation, but at the same time it will do the like main function for your peak shaving, load balancing, and storing renewable. I mean, when you have got additional generation in the system. This is even like another technique, even better function, provide better service compared to the previous one, because the previous one only have the droop and then internal current control, but here you can see there is one more control here, which is low voltage right through. So by including that low voltage right through capability, so low voltage right through, again, I mean, depending on the system grid core requirement, there is the like that for if you have 0 voltage, how long you need to connect, and then from 0 to at some other voltage. So that's like different requirement. So as long as within that voltage range, when you have got that grid fault, so depending on that, this LVRT control, it gonna be producing some reference power, which at the end will be adding these two, and then it will like apply as a reference Q axis current to the inner current control loop, and other one is just like real power, which is at the end connected to the related to the frequency as well. So by if you use this sort of control architecture, so I mean it can actually synchronize and provide active reactive power, as it is using droop control to adjust output power based on the gate frequency or voltage variation. But as I say that during this fall, the system also applied that LVRT logic to maintain the required current and ensure that the whatever either renewable or the battery, it gonna be providing service to the gate without like that tripping. So it actually include that LVRT capability, and as I say, like nowadays many of the gate cord, they demand that if inverter is beyond like certain like capacity, it must have, I think in Australia it's more than like 30. If it is more than 30, then you must have like low voltage right through capability with your inverter. So this one more like if you have got like hydrogen electrolyzer, or as I say, like if you have like other devices, it could be so I mean normally fuel cell, but it could be electrolyzer as well. I mean if you have other devices in the system. So again, I mean the technique would be quite similar, that you will be having that PLL and then that power control, and at the end you will have that output control signal, which is voltage and angle. It gonna be coming your current source control mode. Then I mean it will be connected with the grid. So yeah, so again, I mean the control technique is at the end is same, only difference would be like your whatever devices you're gonna use it. So it's not that any significant difference when you are using like that green hydrogen system instead of like renewables or battery. So again, I mean yeah, I mean only difference would be that whatever the converter inverter technology we mentioned, that gonna be utilized, but overall like the control design framework would be quite similar, but definitely I mean the model would be different. Your at the end, I mean the control parameter would be different as well. Now for using like GFL, I mean the key advantages as like it's quite simple, and as this is massive technology as well. It cost effective because it's easy to implement, and also it's easy to compliance with the grid code as well, because it has been using I mean quite a while. It also need like less computational, less sensing, which reduces the cost and simplify the design. So this is like the summary of whatever the key advances I mentioned, that compliance, cost, maturity of the technology. Yeah, I already mentioned that application, that GFL use your solar inverter, EV charger, wind farm, UPS, and the reason I mean why is used, we already mentioned like that low cost, plug and play, follows grid without anything extras. Synchronization is also easy, and uses like existing PLL as well, but it does have like limitation when, as I said, like mainly when you have got weak grid. So anyway, I mean probably you know already, right, what is strong grid and what is weak grid. How do we know which grid is strong and which grid is like weak? So mainly from the short circuit ratio. So depending on the short circuit ratio value, or other could be like even fault current capability as well at the point of common coupling. So if you measure the short circuit ratio, I think if it is less than the 3, then we call it weak grid, and if it is more than 3, normally we call it strong grid. And there is a simple equation also, you can use like in like y, how to measure the short circuit ratio. So in certain condition, I already mentioned that GFL fails mainly in the when it is like isolated microgrid, like here no voltage reference, converter cannot operate, and when you have got weak grid, you have got voltage sag, you have got unstable current, and then in those cases we mentioned that GFL fails, and we have got disturbance, as I said, like the PLL looks to give like the wrong angle, that can give incorrect power, and then your controller will also provide incorrect control signal that can actually deteriorate the system performance and can introduce sometime instability problem as well. I already mentioned that for weak grid you have got low short circuit ratio, voltage sag, distorted or very noisy grid voltage. So that will indicate that weak grid impedance and poor voltage stiffness typically occurs when you have got like the remote location. But the thing is like that in most of the cases you see most of the renewable energy zone that connect in the remote area, not in the CBD, right? So that also even like make the problem complex, because the weak is already grid, and again we are integrating most of the like large scale when you have got renewables in the weak grid. So that's why we need better control and also like grid forming inverter. Voltage sag that might cause like caused by voltage, sudden load change, and also light impedance, noisy voltage can be coming from harmonics or when flickers from nearby load. Also sometimes it can come from converter that can distort the voltage as well. So you know that although there are so many inverter converter, but you see that many of them does not produce pure sine wave. So always converter, inverter that actually contribute for the power quality problem. Also the different advanced filter, it can address that problem, but again still there is a possibility that it can distort the voltage. And once you have this problem, as I said, GFL inverter may become unstable as control assumes like a strong voltage input. But if you have a like poor, then yeah, it can actually become unstable. It cannot support and disturb voltage. Again, when you have got that weak grid and distorted, as I say, like PLL can fail. So that's also, I think, probably we already talked about what are the root causes of this, like low SAR, distorted waveform, high grid impedance, fast dynamics, voltage sag or voltage voltage unbalance. That is also one of the problem in recent areas also. When we are connecting different photovoltaic system in a different phase, because most of them like in a single phase in your home, right, and people connect in different phases, sometimes that also causes voltage unbalanced problem as well. That's I already mentioned, less than 3. That's normally we called it like weak grid. Yeah, so I think all of them probably we already covered. So now I just quickly show one like simulation result, then probably I'm gonna stop. So here you can see just like you have a system where can be connected with the grid. Initially definitely it's grid connected. Then you have got number of devices like PV, wind. You have got load, but also you have got that green hydrogen system as well, like electrolyzer, storage, and PM cell. But what happens here for this type of study, that when one of them like in operation, other one actually stop. Is any question or okay? So it's not that both alkaline, electrolyzer and fuel cell operating in the same state. So when one of them operate, another one is actually stop. So that's how in this study done. And therefore, I just mentioned like what like different capacity they are using, like, and then like all the model that I discussed yesterday by using all those model, and then here how that your electrolyzer and fuel cell will work. That actually given this simple rule based control, like depending on the power coming from PV, power coming from wind turbine, and then the system load, and then because electrolyzer also that this is a load, right. So by combining of two things, and then what are the like your storage, hydrogen storage, because storage always has like minimum and maximum, right. Like the battery, we have got minimum SOC, maximum SOC. So here also like sometimes people see like 10%, 70%. Between that, it will decide whether your electrolyzer is on, and as I say, when electrolyzer is on, PMA is automatically blocked. So that's like a switched off. And then in other condition, like your total generation is less than the load, and also if it is P minimum, is that the condition, then I mean your PM fuel cell is switched on, and then electrolyzer is switched off. So this is only that rule based control, that how you gonna operate your fuel cell and your electrolyzer. I mean, when you will produce chemical energy, when you will produce electrical energy from chemical, depending on the loading condition, depending on your storage capacity. So by doing that, yeah, again, I mean, this is the same thing that the single line diagram shows, and then it shows like whatever the condition I mentioned, it actually satisfy exactly the same thing, that you have got the load demand, and then how much power coming from solar, how much power coming from your wind, how much power coming from your grid. Based on that, what time your electrolyzer is actually consuming the input power, or when your fuel cell actually producing the electric power. Because in those cases, we need to have the energy balance, and depending on that, how your that storage tank also having the storage capacity as well. So by doing so, you will be able to understand that the model that you have designed, is it making sense? Because at the end, as I said, that all the generation will be equal to your consumption. So that's the one way to also validate your model. And once these are all right, then you can go for other type of study as well. But this is like your minimum things that you can do. So other things I'll just also quickly show another, only here you have got grid following inverter, and this is more like a single machine to infinite bus, but here also there is a load connected. So again, this is more like detail, that your ABC signal, you are measuring, then you are converting, and then you are doing the power calculation, and then you are designing the control. At the end, after having that control signal output, because at the end you are coming back to your main system, you have to again go back to DQ to ABC. So that's actually showing the whole total things. If you want to have that voltage in ABC, current in ABC frame, but if you want to do only DQ frame, then you don't need to do all the calculation. So as Dr. Animesh mentioned yesterday, that once you actually design the control in any form, the first step would be that you just check whether your control design makes sense, and once it makes sense, then probably you can do further simulation, to showing that how your control design is performing, either to control voltage or to control frequency, or other things. So here whatever that design I showed, even number of them available in the MATLAB as well. Here also I mentioned all the parameters. So if you want to check it, you can do this. So here the capacity of the converter is 15 kilowatt, and here you can see that, sorry, here actually we have got 10 to the power 4, so it's here 15 at this point. So what actually we are doing here, we are suddenly changing the reference power. So it was initially 15 kilowatt, but you are asking to reduce that power that you're going to get from the inverter 10 kilowatt. So, if you want to do that, if you make the changes, how your control signal is performing. So, you see this is like the reference, and you can see that it is actually following the reference both like real power and also reactive power. Definitely, I mean, depending on the control, sometime it might track within shorter period of time. Sometime you might have some overshoot. You might sometimes have also some oscillation depending on how good your design. But at the end, I mean, if it is follow that reference, then you will be sure that your design actually makes sense. So, that is the always, I mean, the test that you should be performing after designing the control. And you see that not only PQ, but also that DQ current reference also it follows, as we are giving like 0 reactive power normally. So, that is why it producing 0, but what I am trying to say that it actually following the reference. So, maybe I will stop it, because the other one more like grid forming. So, I will show you maybe in the next one, but here I just put it because at the end I just shown like the comparison when actually you have like different sort of like inertia level. So, here initially it was like 7 SCR, but later, I mean, when you change the SCR, that is the problem. As I said, the grid following fails. So, you see that when SCR is less than 3, the problem occurs. So, that this is rate of change of frequency. So, when you have got very low short circuit ratio, your grid following have the problem. But you see the grid forming is still okay, even the short circuit ratio 1. So, we started 7.5, and then like here when it is very low, this problem occur. And as I say, like how you can measure short circuit, you just need the short circuit power of the grid, which is PSC, and then the denominator one is just the capacity of the installed generator. And how you can determine this power. So, if you know that voltage, grid voltage, and also the grid impedance, also I mean this is quite challenging to measure it, but there is a way, I mean, you can also measure the impedance. So, that is how you can measure the SCR. Always those of you are working like the grid level, it is advised that you measure the grid strength first, so that you will know like the control, everything you are going to be design. Are you designing for strong grid, or you are designing for like weak grid? Because based on that, I mean, you should be choosing your control strategy. And as I said, this is not that difficult. This is one way, but also as I said, like fault current contribution, from that also we can do that. But yeah, I mean, it's better to do it. And as I said that, I mean, once it is, I mean, weak, then we have to go for the grid forming, which I'm going to discuss later. Thanks for your attention.
Thank you, Professor. So, any questions from the audience?
Good morning, sir.
Good morning.
There is one question where you showed one case study, 15 kilowatt grid connected converter. In that grid impedance, what you have selected, that is 4 millihenry and resistance 0.2 ohms. Sir, how did you select these values? Because grid is, we say it is a infinite one.
Yeah, I mean,
For testing at least.
so that's again, I mean, for, I mean, what we did, like for the simulation purpose, just to show like that if you, because I mean, when you have got like, different types of grid, definitely that value will be different. But just to check here that if we change, considering that one initially, that gives like a strong grid, that SCR value. If we have that impedance, that is actually giving that initial value 7.5. So that's the reason we picked up that value, and then I mean we change it and show that, I mean, because I mean what will happen that like that impedance, I mean that equation we showed, again I will just open it. So if you see that, so when you have got higher impedance, that means SCR is low, right? So SCR is low. So we just picked up that value initially, but as I said that there is a way, I mean, you can measure the grid impedance, but here I mean we didn't, we just pick up a value that give that particular short circuit ratio.
Okay, thank you. We'll take one more question.
Sir, in the previous session, you mentioned that harmonics level could be reduced below 5% IEEE's acceptable limits. So, what is the limit for voltage instability, sir, according to IEEE?
So, for voltage, I mean, again, I mean, in different countries, there are many different requirements. In Australia, I mean, for like low voltage grid, we have got, I think, plus minus 5%. But for India, I'm not sure, but should be, I mean, close. But in high voltage, sometimes they consider plus minus 10, but for voltage is plus minus 5 for like low voltage distribution grid. And for frequency, some country it would be like plus minus 0.25, some country plus minus 0.5, like 50.5, and lower is 49.5. But in some cases, like 49.75 and 50.25, that's the limit.
So, for low voltage, it is 5 volts, and for high voltage, it is 10 volts,
Yes.
plus or minus. Thank you, sir.
Okay, thank you, Professor. So, I want to give a heads up that I am sharing the slides, everyone. So, if you see the course plan, the end day we have a 1 hour exam. So, I request all of you go through the slides every day. So, you will have some handwritten exams here, and you will get a transcript on that once you get maybe some credits for passing the course. Okay. So we'll have a 15 minutes high tea break. It's arranged. Please have it and let's meet after 15 minutes. Thank you.
Anyway, don't be scared for getting the certificate. I mean, I think all of you will be able to pass it. So yeah, so it's not like very difficult exam that I have to be worried. Yeah.
Okay, welcome back. So we are going to start our next lecture. And last lecture you gone through this grid following in mostly this grid integration studies. Grid following is a classical control. Now the next emerging control is grid forming. It has several applications, and in this topic we will go through what are the generic application and what are specific to hydrogen electrolyzer, how grid forming technology can be implemented there. So this lecture will be about that. And okay, so it is over to Professor.
Thanks again and welcome back. So many of the things, I mean, in the slide, probably, I already mentioned it. So maybe initially I'll quickly, go, and then maybe later when I'm going to show application, maybe I'll slow down. So again, I mean, like the previous case, this is quite similar content, but again, I mean, this is towards grid forming, and previously we mentioned like the grid following. So that would be only the difference. But as we mentioned like many times, that grid forming inverter are becoming essential components for the grid, and we talked many times that especially for like the microgrid, weak grid, and also like when you have got like renewable hybrid system where you might have hydrogen. So in those cases, I mean, it is essential that you're going to go for grid forming control for the inverter. And here actually, I mean, I did mention some scenarios where, I mean, you might need grid forming. So one of them, I mean, I already mentioned that from fuel cell produced DC, and then we need inverter DC to AC. Now in those cases, if you connect in any of these cases I mentioned, probably you're going to go for grid forming. So also let's say you have like hydrogen powered microgrid, or in those cases, I mean, you can use that grid forming control. Also, I mean, as I say, like when you have got weak grid, its support need for like to ensure stability, mainly when you have got the low inertia condition. And also another important application we didn't mention, that the black start capability, right? Mainly, let's say, I mean, if for some reason if you have blackout, right, and when you have got like this inverter dominated system, that grid forming inverter also can be utilized, I mean, for the black start purpose as well. So not only control, but also in the black start, mainly, I mean, if you that like when you have got like off grid setup, I mean, when you have got the grid setup, there are many other devices can contribute, but in off grid, as you see, like mostly renewables and converter. So in those cases, I mean, the grid forming inverter also can contribute, I mean, to restart the system as well. So the other scenario also, as I said, like the renewable hydrogen hybrid microgrid, in those cases also, I mean, when you have got like solar, wind, and hydrogen storage, all of them operate together. So in that cases, I mean, GFM can contribute not only for power delivery, but also to maintain the system stability as well. And again, it's like the advantages is that, I mean, it ensures seamless renewable energy powered hydrogen system, and also it, when you have got hydrogen microgrid, it also ensure the grid transition, because that is actually quite important. Like if you know like the microgrid, it should be having capability to operate both grid connected as well as off grid, and during this switching from connected to off grid and vice versa, there is a like a huge actually transient in the system. So that time also, I mean, you must need like grid forming to ensure that transition between grid following and grid forming, and definitely it maintains voltage frequency even like in your hybrid system when you have mostly like in the renewable generation. So other scenario could be that you have like hydrogen powered backup and emergency system, where also like for example your fuel cell provide emergency backup instead of like diesel. So in those cases also I mean GFM can ensure immediate and stable AC power during outage. And remote microgrid for I mean remote community, I mean we already mentioned that could be also other scenario where you will be using GFM. Sorry, here it's in most cases we are saying like GFM, but here same thing like grid forming actually inverter, but we miss the M here. So it's again I mean I'll correct that one. So we already I think mentioned all of them. The requirement for low inertia grid, renewable variable, block start, hydrogen power, hybrid system, and to maintain the grid compliance, I mean we need grid forming, and in both cases they like address those scenarios by providing synthetic inertia, maintaining voltage frequency, restart grid or microgrid after outage, ensure stable operation of fuel cell, and definitely meet the voltage frequency and also low voltage right through as I mentioned. Again I mean we already mentioned like that what is grid forming. So again I'm not gonna repeat again. So it makes the inverter act like a voltage source that leads and stabilize the grid. So it's again I mean as you remember in previous cases we mentioned that follows, but here actually that leads, not just following the grid, and it does sets the voltage and frequency reference. So it's not like again I mean just following the grid and injecting power to the grid. So it establishes a reference for other grid type device. So even like microgrid, let's say you have got some grid forming, some grid following. So the grid forming one will actually provide reference to the other grid forming. So grid forming will follow the grid following like when they are like operating off grid condition. And as I said that it operates without external synchronization. In but previous cases we need external synchronization. We don't need any PLL here, and it regulates voltage frequency actively. So here as I say that this one the inverters, that's like would be the like the leading is not like the following that in previous cases that we mentioned. And here you can see that we don't need any external PLL I mean for synchronization purpose. So that's the main difference with the previous cases. So that slide probably we already covered. No PLL required for doing the synchronization. It internally generated the voltage reference and derived from like that virtual synchronous machine voltage group and also grid forming algorithm. And it already mentioned that it operates well in isolated or grid forming conditions. So here I mean even like in the current control loops that I mentioned previously, but here what happened like that current mode control in GFM like inverter regulates the output current based on the internally generated voltage reference. So that's actually maintaining the system stability while supporting like voltage and frequency as well. So the outer loops again I mean that's mainly the voltage, and then the inner loop, that's the current. But again, I mean that PI controllers, again, I mean we use even for grid forming as well, and as I said, it use most of all the devices. But the outer voltage reference is derived from like a either a virtual oscillator or like a droop control logic. It's not like coming from external grid. So that's I think the main device. But other than that, again, I mean from like whatever getting from inner control loop, we use as input to the PWM for the inverter as input. So here, I mean only where that's a difference like that how we are generating the reference, but in terms of control algorithm, here also you can use like instead of current, here you can see this is a voltage source, but other than that, droop control also used here, but here also we use like PSC, which is like power synchronization control, synchro converter, which like making the converter like a synchronous generator, VSC, like also people use like meshing control, and also virtual oscillator based control technique. That's also used for GFM as well. So there are some algorithms similar, all the input is different, but some other, I mean the new technique as well, but these are not all the techniques that when Dr. Animesh discussed yesterday, I mean that can be utilized here as well. But so the main things like that you are trying to mimic the characteristics of the synchronous generator. That's the like main purpose here. So like others, like droop control, again, I mean it regulates voltage and frequency using frequency and voltage droop. VSC, it enhances the droop control by emulating the inertia and damping through the machine swing equation, which I believe all of you know. Power synchronization control, that uses active power feedback to regulate the phase angle directly. Synchro converter, that precisely replicate the synchronous machine within an inverter. So that's why name is also like a synchro converter. So it's not synchronous machine, synchro converter. And then voltage oscillator control, that actually applies like a nonlinear oscillator model to generate GFM voltage. So those are the like mostly used technique that you will find in the literature. So this one nothing to repeat. Again, I mean that's like droop control, that trying to emulate the synchronous machine behavior by adjusting voltage and frequency based on your real and reactive power. Same technique, you just need to use or find those droop, and it's a single parameter, it's not that difficult to find it out, and then you are giving like your voltage and frequency control loop. Again, that's gonna give you your theta and voltage reference for the like inverter to operate. So in previous cases we applied, but here you can see that we are producing the reference, I mean to from the grid. Again, I'm not going to repeat because I already mentioned that what are the advantages of droop, mainly for the simplicity. And again, I mean in most of the cases it actually works fine. Only your droop control have problem when you have got like unbalanced situation. Unbalanced situation actually does not provide like your desired performance. So when you have got unbalanced load, and in microgrid in other cases you could have unbalanced load, and also like if you have a microgrid or like weak grid, and if you have a like a not like symmetrical fault. I believe you know symmetrical and unsymmetrical fault, right? So when you have got fault like in 3 phases, we call it symmetrical. But if you have fault like one line to ground or line to line, in those cases, I mean droop control performance is comparatively poor. So if you see like your system that you are working on is not actually balanced, then you will go for other control technique. And when your system like heavily nonlinear, fixed droop coefficient may not handle all grid condition as like a PI control. So you might need to change the droop coefficient when your operating condition changes significantly. And other problem also, in many cases, it's provide steady state error, like both frequency and voltage deviation. Always our expectation that steady state error should be 0, but that's also like problem. But there is a way that actually you can enhance the droop control technique as well. Not like that you have to always use that like standard power, frequency, voltage, reactive power. So you can have like adaptive droop, which is gonna provide variable droop based on your system condition. So it's gonna change the droop parameter. Also, droop parameter is like a primary control, right? You could also have like secondary control. That secondary control gonna give the reference to the droop when the system condition change. That's how your overall microgrid or whatever situation you have, even using the droop plus secondary, sometimes you also have tertiary as well, but up like up to secondary in most of the cases is fine. So using that secondary control layer, I mean you can restore like the voltage and frequency when your only droop fails to do so. You can also like integrate with virtual inertia, predictive control, and other either communication less or communication assisted, like centralized, decentralized. I'm not going that far because it's not like a control course, but using like both centralized, decentralized, or even like recent year also you have got distributed as well, because the centralized, decentralized both have their advantages as well as limitation as well. Because centralized, what happens like you have to collect signal from all the devices you have, then you process your control, and then using communication again you have to send back the control signal to all individual devices. So when you have got multiple devices, and if your communication is not reliable, for example, let's say communication fails, then you cannot give signal back or even collecting the signal from that well. So that time your system performance might deteriorate. But also decentralized, you don't need communication, but the problem is that, for example, here if you have got one electrolyzer and another electrolyzer is other location, they cannot communicate, they cannot talk with each other. So they only know what is happening in a particular location. So only based on the local control signal, it will produce the control action. But the hybrid, so the distributed, it use some communication, but only communicate with the nearby devices. So for example, you are here, you only talk who is your like a left and right. Someone like quite far from you, you are not talking with you. But the next one, he is like talking with the next body somehow. So we have got some limited communication, but at the same time, it doesn't need to collect signal from everyone. So people are nowadays also doing like distributed as well. So again, but that's for mainly the secondary level control. So VSC, I mean, again, I mean, although we talked for the previous cases as well, but again, I mean, the way that we are like, you know, designing slightly bit different based on the signal that, I mean, we are using here. So as I say, like the from the droop, you're gonna get those like, you know, input, and then you're gonna apply in your VHG control. Now how we can design this one? Again, based on these two simple equations. So this one, that swing equation, and this one is just like your you know, internal EMF in the synchronous generator. Now synchronous generator also, I mean, you know that sometimes we model first order, sometimes we model second order, but also you can go like, you know, fifth order, seventh order as well, but depending on your requirement you go. But for this sort of control, you know, first order, second order is more than enough. So by just using these two equations, you can actually you can see here, sometime you are adding, you know, sometime you are dividing. That's how you are just implementing this equation. And then at the end, when you have got d omega by dt, and then you are doing that integration, that's how you will getting your omega. So our here our intention to get omega, and here our intention to, because that's the variable, that's the voltage, internal voltage. So once you rearrange this equation, put everything in the left hand side and put all our other side, and then if you just develop that block, you can easily develop this two block, and that's how you're gonna get I mean, your, you know, the angle and voltage which we need, I mean, for your grid forming inverter. And as it is using like, you know, damping, inertia, droop coefficient, that's how it's going to be trying to mimic the characteristics of the synchronous generator. So the PSC, the third one, that again synchronizes the inverter with the grid by regulating the power flow rather than, I mean, tracking the grid voltage. So here again, I mean, you see that by this angle it's gonna be synchronizing, but it's not, I mean, it's not following the grid angle, which is does for grid following inverter through that PLL. So it actually producing that angle, I mean, that gonna help, I mean, to synchronize with the grid. Now the controller again, that's you see that compares active power, and then you know, by using that's like a, you know, integrator, it producing that theta, and then finally from that, I mean, it gonna be giving the command to the grid forming inverter. Now here it's just the comparison, these three so far we have talked, which one you know, provide which function. So for example, the grid forming, islanded operation, inertia emulation, in terms of also complexity, which one is good for weak grid. So this is again this one like PLL based, which is grid forming. So that's why you see many cross here. But normal like the PSC one that we talked about, again, I mean, we did not use that swing equation, so it cannot actually emulate the inertia for the system. But these two can service like the other operation that's needed. So the one that I mentioned, that synchro converter, that exactly emulate the full dynamic behavior, not only swing equation. Because if you remember VSG, it only takes the swing equation, but for this one, it tried to emulate the full dynamic behavior of the synchronous generator using that power electronic converter and the control logic. So that's the biggest difference. So although here, again, as I mentioned, depending on what sort of model you're gonna use it. So as I said, like it might be like, you know, sometime fifth, you can go up to like a fifth order model, electromagnetic. So if you go like all the equation that is gonna be coming here, you have to use all of them, and through that, I mean, at the end, I mean, you will be developing all the block at the end. From that, you're gonna get your power, and then you're gonna be applying again for that things that we mentioned from your inertia. So the inertia things coming it here, but all the voltage equation you're gonna be solving, and then that's how, I mean, at the end you're gonna be getting the power. So from that, it is a little bit complex, but it's not that you cannot do it. So you just need to first think like that, what sort of synchronous machine model you're gonna use it, and then based on that you're gonna write those equation, and then from that you will be finding power, and then, I mean, from that, I mean, you can, and then our desired signal again, I mean, that omega theta, and then we're going to apply that one to the converter. So here again says that, I mean, it's not only like electromechanical, that's only for damping and swing, but also like electromagnetic, which actually does involve internal voltage and current dynamics, because we are trying to capture like flux, linkage, and also rotor interaction. So to do that, actually you have to go for higher order model, and also this inverter computes like virtual torque from power deviation, then integrate to obtain the virtual rotor speed angle, and then use it to generate the voltage waveform that you can although, I mean, we haven't shown all the step here, because it's going to take like long space. I mean, if you want to show how you can rearrange the model, but the thing is that you just need to rearrange the model. That's, I mean, you have to do it. So again, as I mentioned, that it does consider everything that you will be seeing in the synchronous, like rotor inertia, swing, internal EMF dynamics, governor, turbine, excitation system. So everything that's part of the synchronous generator that you're going to be considering to provide through this synchro converter, virtual rotor dynamics, all that happening inside the damper winding, mechanical input frequency, because the governor mechanical, this one normally does regulate. Normally in synchronous machine we use like AVR, automatic voltage regulator, that also be included here in the synchronous converter as well. But on top of synchronous machine, sometimes it's also include like FRT for providing low voltage right through support for the converter as well. Now other one, as I mentioned, like meshing control. So the meshing, again, I mean, both like meshing control and also like voltage oscillator control are PLL free for the grid forming inverter, that enable inverter to generate voltage and frequency autonomously, that support to establish the grid. And also this is like a decentralized, you need like, you don't need like communication as well. So meshing control is therefore designed to utilize the device level similarity between power converter and synchronous machine. This is like, again, between these two, they actually try to like mimic the behavior. So that's how they actually mesh with these two, just to provide like provide the grid voltage behavior. And the other one, voltage oscillator circuit. So here, without like using any PLL, it emulates like a nonlinear oscillator circuit to generate like a voltage waveform. From that one, we generate that voltage waveform, the oscillator, and then we apply like across multiple inverter using that inherent oscillator coupling. So that's how I mean it produces the voltage, and then we use for GFM. Now in terms of application, again I mean we already mentioned many times that it can be used. We already mentioned that hydrogen system, but also I mean we already mentioned that this one already many grid. Even in Australia we do have number of grid forming BS already in operational. Renewable it might happen in coming years, but so far they onset it only for battery. For the battery, I mean this is could be that architecture we might use. If again I mean this is, you see this is again that swing equation. From that we got theta v, which is producing reference from inner control loop, and then through PWM we apply your inverter to generate whatever voltage and frequency we want. But it can be used for hydrogen system as well, not only the battery, although the battery is already using. But here you can see that's how probably that's how we can use for hydrogen, like from hydrogen production. If you use DC and then DC to AC, then I mean you can use that one, and this could be like simple control, but other controller that's also mentioned. It can be applied for hydrogen based system, which might be, although it's not happening now, but it might be working as grid forming control in coming years to provide that grid stabilizing service it might need when you have got large scale green hydrogen system will be connected, grid connected. So if you have like separate off grid system, that's defined, but when you have got large scale, definitely grid will also provide requirement that unless you provide that grid ancillary circuit, you will not be allowed to connect with the grid. So but that's actually I mean possible. So this one showing one example that if you want to do it for fuel cell system, that's how I mean like here like two parallel system that's having SOFC types fuel cell with like grid forming control. So that's how I mean you can design then, and if you are working in this area, probably you can try I mean this sort of architecture as well. So as I said, in coming years maybe you will not have a single system, you will have a multiple system. So you can consider not only single type fuel cell, you can also use different type fuel cell that we mentioned previously, because definitely it's not that all the installed system would be PM, although that provide better performance, but you will having the other system as well. So it's good to do like several scenario analysis that I mean you can do it, but here just showing like one example that also you can do. So again I mean we already mentioned what are the key advantages. So black start, if your grid impedance is high, grid is weak, and then you want to emulate inertia, and then for islanded operation as well. That's we already mentioned that weak grid it cannot handle. Now that GFM have already been deployed, as I say, like in many application already. So it's not only that's now like a research, already like in the implementation phase. But having said that, still I mean there are many work has to be done. I mean to get exactly the behavior that we are expecting to get it from grid forming inverter stepping, because this is just like self-explanatory. You can do that, but in Australia, I mean, we have a number of project that already really implemented in the power grid. The inverter type they have used, but as I said, all of them have the battery, and all the project they have got function like this one, providing like the fast frequency response, because in Australia like we already have frequency ancillaries market. So if let's say if you own the battery, and when the market need it, and if you participate in the market, at the end whatever service you're going to provide, you're going to be paid back. So that's already happening. So that and many project that people are doing, they are not only using the battery to store energy and provide power during the peak time, but they also sometime participating in the market and making money. So that's how, I mean, all the battery is expensive, but that's how probably when you have got multiple application, I mean, you can make sense that it's not only technically but economically feasible. But if you just, I mean, think about single application, then battery is still expensive device. But when you consider like multiple application, then I mean, it will make sense that you have battery. So in Australia, as I say like that, there are also many company for virtual power plant. So if you just make contract with them, you're gonna be also paying monthly, whatever the agreement you have through battery. That's how also you can make money, but at the same time you are also helping the grid as well. But on top of that, you are also making money. And this other project for islanded operation battery, and then this one mainly to provide synthetic inertia and fast frequency response as well. And this one is more like the storage for grid stability. Again, I mean, how I'm going with the time. So again, I thought like because last time one of you mentioned like to showing the comparison between battery, but this one like because the fuel cell electrolyzer more of the load, right? It's not generating any power, so you can just control the input power like as a control load. But here like when you have got electrolyzer, it does produce electrical power. So here like in this simulation just shows like that when that you need to, for example, let's say maybe I know you are asking to provide additional power. Now how, but now here this is like the hybrid system. This is not simulation like separately battery and fuel cell. So what that showing that when you have a hybrid system and there is a need and you have got both battery and fuel cell, so how both of them are responding. So definitely here you can see that which one is performing better here. Definitely, I mean, you see that the battery response is quicker, right? Because if you see here, sorry. So whenever need is immediately almost like exponentially it's giving the power, but here slightly, but why it is going, because that time, because this sudden support we need only during the transient, because here we have a grid, right? Later, I mean, the additional support, and when also you have got power from fuel cell, so battery is again, I mean, we don't even want to utilize that time, so battery power is again like going from discharging to might be negative, that means it's going to charging phases. But what I'm trying to say that if you have a like a hybrid system, sometime I mean it's gonna be giving better service. Although I mean I showed one example, but here also the same system, like when your SCR is less than 3, you see that I mean the system collapse is going like unstable, but when you have like grid forming, it's again going back. But grid following, it cannot do not only that system. I mean in most of the system, I mean when having that SCR low, you might have problems. So again, I mean this is like a very hot topics. Not only like in Australia, I know many countries now they have so many work is going on. In Australia, you will find most of the power industry now their main focus like I mean how we can improve that performance that we are getting from grid forming inverter. So again, I mean machine learning and that AI or reinforced learning, that's always like hot topics in different area. So very few like droop control or VSM that I mentioned. To tune that parameter, you can use that one. Hybrid, I mean how like GFM and GFL like working together. So for example, let's say if you have 100 inverters, how many you need GFM, how many need you GFL? I mean what should be the ratio? Still I don't think there is any like established method that you can say that I need 5 GFM and 10 GFL. So still I mean how you gonna use it, how they you gonna coordinate them, how when you have got 100,000 of them, I mean how you can operate together. So and also what are the different topology for inverter and what are the different mesh system. You have got radial power system. So depending on like different things, I mean there are still many works that need to be done. So here actually I put number of research question I'm gonna share with you. So those of you are interested, this gonna be give you enough to think on what actually you can do. I mean if you are really interested to work in there. I mean I could discuss, but if I want to do one by one, it might take another hour. But I think the research question is given, how to find the answer, that would be research. But sometime finding the research questions for those of you are doing PhD, it takes 1 hour to do the literature review, finding the problem, and then asking the exact question. That once you have the answer, you will have something new that gonna contribute to improve the power system performance. But at the same time, you can also publish, you can improve your track record, and that gonna be crucial for your future career as well. So I'm gonna leave it with you to read, and if you have research scholar or if you work by yourself, you can pick up anything that messes with your expertise and also with your future research direction as well. With that, thank you. Hope now you have got some idea like how this grid following, grid forming works, in which situation you're gonna be use what type of inverter, what type of control, right? And then as I said, although I didn't discuss, but that's gonna give you some things to think about, and then going from here. Thanks for your time.
Thank you, Professor. So we'll take questions after noon. So all of you are requested to leave for lunch. So 2:15, please gather here. We will have a photo session. Some guests will be coming, so please be on time by 2:15.
And anyway, I mean, today is the last for device level. From tomorrow, we're gonna go more like the system level, like
So
the micro gate.
power system people will enjoy
Yeah.
more from tomorrow.
So
Okay.